This video is for topic 8.6, molecular structure of acids and bases. The objective for this topic is to explain the relationship between the strength of an acid or base and the structure of the molecule or ion. Up until this point, we've pretty much gone with memorizing our list of strong acids and our list of strong bases, and then saying that anything that's not considered strong is automatically weak, which still applies. But in this topic, we're going to specifically look at how that molecular structure really determines whether something is strong or weak, because it's not just something that we memorize, it's also important to know why it happens that way. So it all comes down to the protons in the molecules, okay, because that's what's going to be participating in the acid-base reactions. So acids are going to give up that proton and bases are going to want to accept that proton. So if we remember our definitions of strong acids and strong bases, strong acids are going to want to give up all of the protons, which means it wants to stay in its conjugate base form, okay? It wants the conjugate base is going to be the preferred form of that molecule over the protonated acid. A base is going to be the opposite. When we think about our hydroxide donating bases, bases are going to want to stay in that hydroxide form, okay, which means that that conjugate acid there is going to be the preferred form of the strong base. When we think about whether something's going to be strong or weak, we need to think about their molecular stability. So we're going to go back and we're going to lean on our knowledge of electronegativity, resonance, and what makes molecules stable, because it's all about the conjugate form. If something is more stable in the conjugate form, it's going to be strong because it's less likely to reform that original acid or base. Remember, strong means complete ionization, complete dissociation. So if you have a really stable conjugate acid or base, that means it's a very weak conjugate acid or base. It's not going to want to either accept a proton or donate a proton, which means the original acid or base was strong. Let's look at some examples. So let's look at our strong acids and bases first. So if you think about our strong acids, they all contain anions that are highly electronegative, and therefore they're pretty content to stay as an anion. So hydrochloric acid, for example, HCl. Chlorine has a high electronegativity, so the fact that it has to carry a -1 charge is totally fine because it is a fairly large atom and it has a high electronegativity. So it's okay holding on to that additional extra negative charge, that extra electron. So it's a very stable ion. Therefore, it's not going to go back. It's not going to act as a base to regain, recapture that proton, recapture that hydrogen to go back and form HCl. So it's very, very stable in its ion form. Therefore, HCl is a strong acid. When we think about our strong bases, all of our strong bases are hydroxide donors. So hydroxide is a super, super weak acid. So when a strong base dissociates, the conjugate acid would then be OH. OH is a super, super weak acid. That hydrogen and oxygen are not going to separate, and therefore it's very, very stable in its hydroxide form. So because it is a weak conjugate acid, that means it was a strong base originally. Let's look at our weak acids and weak bases. So carboxylic acids are some pretty common weak acids that we're going to see. So a generic form of a carboxylic acid is an R group, which can be literally anything you want. It's typically some sort of carbon chain, probably with some nitrogens, maybe some sulfurs, but it can be anything you want. The key part of this is the acid piece, which is that C double bonded to the O and then single bonded to the OH. That's what makes it a carboxylic acid. That H on the OH group is the hydrogen that's going to act as that's the acidic hydrogen. That hydrogen is going to leave, thereby making a negatively charged oxygen. Now, that molecule has resonance, so that double bond can be between either oxygens, and the negative charge can be on either oxygen. Because of this resonance, that makes that a fairly stable structure, but it does give different opportunities. It can act as a base pretty readily because either form can reaccept a hydrogen. Therefore, since it has some ability to act as a base, it has a somewhat strong conjugate base and therefore would be a weak acid. When it comes to weak bases, nitrogenous bases are pretty common. So one that we see a lot is NH3. Ammonia is going to accept a hydrogen to become the ammonium ion. When we look at weak bases, specifically at nitrogenous bases, we have that nitrogen, which is going to bond to 3 different R groups, which again can be anything you want. Oftentimes they're hydrogens or small carbon pieces. In DNA, you'll see nitrogenous bases in there. And the key with this is that lone pair of electrons. That lone pair of electrons can then bond with a hydrogen to form a positive charge on the nitrogen. And that's what gives it its base form. However, because that does result in a partial charge, it means it can fairly readily give up that hydrogen to act as an acid. So because it can act as both an acid and a base fairly easily, it is considered a weak base. So that's how we can think about our molecular structure and stability to help us determine why something might be considered strong or weak.